Anyway, the next thing in Calc 2 would be to talk about solids of revolution and trying to find, like, what is the volume of an object that has some sort of rotational symmetry along some axis. So you can always do that, but again, if you have something more interesting or pressing or just feel like it, we can do something else. Alright, what I'm going to look at is I'm going to take an equation, y equals negative x plus pi plus the sine of x. Do I want 2 pi? It's not really going to matter, but it'll be slightly easier. Let's see. Let's just take a look at how interesting this thing is first and see if I care. Yeah, that'll work. Let's make it 2 pi. Alright, so y equals negative x plus 2 pi plus sine of x. This is a graph which I'm going to stick to quadrant 1. It's going to be revolved around the x-axis, and we're going to find the volume of this solid. Remember, all you out there, do hydrate. So we want to find the volume of the solid. Again, the thing itself, if we look at the graph of this, it looks something roughly like this. Nope. So close. Alright, roughly speaking, because this is going to be a terrible graph, but it's cool. Again, we only want the stuff that is in quadrant 1. That's like this. And then this is going to be revolved around the x-axis like that. So this area here, it's going to be revolved around the x-axis. It's going to make a solid shape, which according to what I have drawn here, start that over. According to what I have drawn here, looks sort of like a Hershey kiss if we were to revolve this all the way around the x-axis and make a solid shape. So it's going to have this pointy part over here. It's going to expand out both top and bottom and then kind of flatten out to have an edge. If I can, I will attempt to draw this quite horribly. Alright, so these will be kind of like the contour lines of this particular solid. And if we drew like lines here to kind of give you a sense of what this thing looks like. It looks something like that. Then we'd have backside coming around like this. And again, it would have all of its contour lines on the backside as well. So we want to know what the volume of this object is when it looks like that. Okay, so the basic idea here is that we have some sort of figure which you can do basic calculus on, where you can find the area of a cross-section of this thing. Now, this is actually not quite this big. Right? The width of this rectangle is going to be dx, so it is infinitesimally small. I'm just exaggerating it to make sure that we can understand what it looks like. And the height of this particular thing is going to be the function value f of x at that particular point. If we want to, then we can evaluate the cross-sectional area of the shape as the integral of f of x dx. This is not surprising. This is what everybody's been doing in Calc 1 for like the last month or two or whatever at the end of the class. This is one of the weirder parts of Calc 2, however, because people are like, oh my goodness, now what's going to happen? It's really not actually that hard, but it takes some getting used to in order to make sure that you understand what's going on. Okay, so now we have the area of every little rectangle that we can make underneath this function inside the red area. And we have to find the limits of integration. This is going to start at 0, like we have here, right? And then it's going to go out to wherever this point is here. We'll call it B. I mean, over here we can also call this one A, so that it goes from A to B. No matter where it is in the plane, it's always going to end up coming out to be the same stuff. So, what are A and B for these particular functions? Well, A is 0, we already talked about that. And B is some unknown value. But it's, again, not difficult. Once you know trig, alright, this is not hard. We need to figure out when or for what value of x are we going to end up getting a 0 for y? Okay. Right? It happens to work out in this particular case that if x is 2 pi, then we end up with sine of 2 pi is 0, and a negative 2 pi plus a 2 pi is also 0. So did I work that out kind of magically just by doing it? Yeah, sure. Let's be honest, I manufactured this question to be as easy as possible in that respect. I had actually plugged in just the number 7 up here before, and then it came back with some nonsense, and I was like, well, okay. It could just be literally y equals negative x pushed up a certain amount, and then get a sign, or get a function value that has a 0. So sine of that particular value, the sine of this same value with a negative out front of it is just going to end up, these things will cancel out, and then this one will just be 0. So what do I do? Okay, it's sine function. Cool. Again, it's the easiest way to do this. Those of you out there who are teachers looking for ways to come up with questions. Sorry, I completely kept that behind my head. Those of you who are teachers looking for ways to develop questions, that's pretty much how most of us math people do it, is like, find the answer that you want and then reverse engineer everything so that it works out nicely. Or else, come up with a random question and live with the consequences. Because I do that one too. I don't recommend it. Alright, so if we want the volume of a 3-dimensional shape now, instead of just the area of a 2-dimensional shape, what do? Well, this is actually going to end up being a series of individual cylinders that are going to be built one on top of each other. And those of you who do 3D printing, that's pretty much it. Alright, we're going to look at what is the now volume of every cylinder that we have, whose height is now dx, and whose surface area is now going to be the integral from a to b of f of x dx. No, sorry. A. The area... Sorry, I had to think about that one for a minute. There we go. So basically what we've got now is this strip here is going to be the piece around the outside of the circle where we have this rectangle, which is an f of x by dx, just the same as this blue rectangle was here. I should probably actually write it in blue, because that would make it much easier. Why don't I think of these things? Okay. So this blue rectangle here corresponds with the blue rectangle up top. And actually, right, technically, this is inside, so let's make it dotted. And this is on the surface. So this is a height of f of x. This is a width of dx. The width is now going to be the same as the height of the cylinder. So dx is going to be the height of the cylinder. F of x is the radius. So how do we get volume for a cylinder? Well, that's going to be pi r squared, the area of the face, times the height, which in this case is dx. So we end up with pi times the radius f of x squared times the height of the cylinder, dx. And now we're going to take that over all of the possible cylinders that we can make from A to B, which means we can integrate. So find the sum of all of the individual volumes created by these cylinders. This is also known as the disk method. Can also be called the washer method. In this particular case, we don't have a washer, we have a disk. However, all that would be required for a washer is for the center here to have like a hole in it. In which case the radius ends up being the difference between the inner and outer. So let's back that off before anybody gets confused, but if we wanted something like that to then be rotated around the axis. And actually, let's back that off. Let's make the y-axis not the same. Or x-axis. Let's make the x-axis not the same as the location for these things. So this thing would kind of look like this. And then it would come around the outside like this. It would look the same on the bottom side. Okay. Anybody who's been here for a while, you know, probably used to my ridiculous stuff here. And the inside would end up looking like this. There's like a hollowed out portion in the middle where this exists. Actually, right, this isn't connected either because I intentionally made it okay, so this would then come like that, this would then come like that, and then we'd have like this flange on the outside for that part. This would come here, and the bottom one would be more like out there. Oh man. Yeah, I really borked it. Alright, whatever. It's cool. It's good enough. So we get some sort of flange piece like this, which again has a hollowed out piece in the middle, which looks like this. Right, and keep in mind that this is all the way around. So like this hollowed out middle part is the exact same all the way through. It's a bit like, gotta have an object around here, right? There's gotta be something. Something that goes through. Like a film canister. Half of you probably don't know what that is, that's fine. The other half are going, hey. Man. man, no dice. Alright. You know, it's amazing the crap you accumulate after 15 years. I'm sure it's been longer than that. Really? No, I guess not. Alright, cool. I would think that I would have like some sort of object that would be, you know, kind of regularly shaped, but also have this possibly weird property to it. But yeah, I'm not finding one in here. Now we're on to the entertainment portion of the section, where Obi digs through his desk. Great idea. Perfect content. Alright, anyway. Now that I've wasted time on this, that's fine. Yeah, so we'd have something that looks like this. A little lip around the edge like that. Actually this one tapers off to nothing because these two functions actually do connect right at the end. So this does taper off to nothing. There's the possibility that if the two functions did not connect, so you had something that looked like that and something that looked like that, right, then what would happen is this would come around like that, and then this would come around like that. We'd actually have a lip here all the way around the edge. So this one tapers down to nothing. We get, yeah. Okay, so this is the disc or washer method. All that really replaces this middle part here is that we get an f of x minus g of x inside of the parentheses that gets squared when we're talking about the washer method, where there is actually a hole in the middle. And again, those are these over here. Sorry. Oh, I'm gonna regret this, aren't I? Okay, so yeah, I'm probably going to regret this. So with our function f of x ending up getting squared inside of all of this, this is going to cause this trinomial to expand out quite a bit. Hooray! Luckily, we do have the numbers for that. If you check out right here, let's say n equals 2 on, nope, nuts. It's not in this one. Okay. I was hoping I had it, but I don't have that one. Because this is our three-dimensional with, oops, this is our three-dimensional squaring. Actually, come to think of it, I do have it, don't I? Yeah. Okay. So it's where it says n equals 3, and we've got 1, 2, 3 levels that are all connected here in the black. The first one is 1, the second one is 1, 1, 1, and the third one is 1, 2, 1, 2, 1, 2, going around in a triangular fashion. So that is the shortcut, if you wanted to have the shortcut for what we need when you square a trinomial. So we need every possible combination that we're going to get there. So this is going to go from 0 to 2 pi. We have a pi that is a constant on the inside, can be multiplied on the outside instead. That's a free move. And then we want f of x to be squared. So negative x plus 2 pi plus sine of x squared dx. So here, each of these individually are going to be squared. And then every possible combination of 2 being multiplied together are going to get multiplied together, and then we get a 2 for a coefficient out front. So it's going to be pi times the integral from 0 to 2 pi of negative x squared plus 2 pi squared plus sine squared x plus, now we get our twice each combination. So here this is going to be like a minus 2 times x times 2 pi minus 2 times x times sine of x and plus 2 times 2 pi times sine of x dx. Yeah, that wasn't nice, but it's my own fault. Alright, so we get pi times, now we're doing integral of all these individual things. So here this is an integral of x squared, which is going to be 1/3 x cubed. So if we're doing integrals, it's the antiderivative, or this is a power rule. So power rule for derivatives, you bring down the exponent, and exponent decreases by 1. So to anti-derive that, you are going to bring up the exponent, bring up the coefficient to an exponent, and it has to be the next number up. So we have a 2 that's going to go up to a 3. We need to bring up a 3. We don't have a 3 to give, so we need to make it a 1/3 out front in order to balance all this out. The long version of that is that the integral of x squared is going to be dx minus 1 point. Alright, the integral of 3 times x squared dx, but this 3 just can't appear here. We need to then balance it by making this a 1/3 out front. 3 times a third is just going to be 1, which is what we had to begin with. I always recommend doing this like coefficient thing when you're first learning how to do use substitutions or yeah, all this stuff. If you need something to appear out of seemingly nowhere, write out both coefficients. So a 1/3 times a 3, you need the 3, that's going to come in. Go that way. Alright. So this is going to be a 1/3 x to the third plus a, this is just a constant, so this is going to be 4 pi squared times x. Alright, plus, this is going to be the slightly harder one. We have, actually it's not that hard, but sine squared of x. You don't have anything that you can make into a dx term here. Like, you have this dx here, but when you're taking the integral of sine squared dx, if you want, like, sine squared of x dx, man, you're doing okay, I promise. You can't say like, okay, let sine of x be u, because then if you just say, okay, this is u squared, where's your du? Well, your du would have to be the cosine of x, but you don't have a cosine. So you can't just make one appear out of thin air. If you tried to, it would be cosine of x over cosine of x. But now you've got an extra secant in there, so that's not going to work. The easiest thing to do with this is actually to do a power reduction formula from trigonometry. What do I mean by that? Well, use your double angle formula that you had way back when. Cosine of 2x is equal to 1 minus 2 sine squared of x. Rearrange this and make this a sine squared of x. 2 sine squared of x is equal to 1 minus cosine of 2x. And then we don't have a coefficient, so replace this over here, just sine squared of x equals 1 minus cosine of 2x all over 2. And then if we want to take the integral of sine squared of x dx, we can take the integral of 1 minus cosine of 2x over 2 dx. This is actually much easier. It doesn't look like it, but it's much easier. So we can take these individually. You take the integral of 1 over 2, 1/2. So this is going to be a 1/2 x. Then over here, this is going to be a integral of negative cosine of 2x over 2, or negative 1/2 cosine of 2x. So this is the integral of 1/2 dx minus half cosine 2x dx. Alright, the 1/2 isn't doing us any favors here. If we want to replace 2x by u, then again we have to say what's du going to be. Du is going to be 2. Or 2 dx, rather. So then how do we get that into here? Well, dx needs to be multiplied by 2. But we can't just get that out of nowhere, so again we have to create another 2. And then balance it out by also multiplying by 1/2. So that means that this is going to become a negative integral of 1/4 times, this is now cosine of u du, because again we let u be equal to 2x, and then du has to be 2 dx. So we have a 2, we have a dx, those are going to combine into du. If you are ever a student of mine, don't ever let me catch you saying that dx is going to be equal to 1/2 du. Whereas that is technically mathematically correct, it is awful when you do notation, because when you go through this, especially at some point in the future, if you find that something is like a function of x dx, then you're dividing by x, and now you're mixing variables. So like du equals, or du over 2x equals dx, and now you can like try to do, don't mix variables. Don't try to think that you're going to cancel them out and make it work right. Don't do that. Alright, find a different way. Alright, so we get the 1/2 x, and now here with the negative side we got negative 1/4. Integral of cosine of u du is sine of u. And in this case, u again was just 2x. Alright, so then this part here is going to be a negative 4 pi x, which then we take the integral of that, and integral of negative 4 pi x. We're going to do power rule here. Negative 4 pi is just a constant. We need to take 2 from out front from the 4 and use it as an exponent. So now this is going to be a negative 2 pi x squared. Alright, next one. Less easy. Negative 2x sine of x. We're going to have to do what is called integration by parts. Actually, come to think of it, is that a future section? Or is that a past section? I don't even remember now. Alright, let's check table of contents. Yeah, it is. It's technically a future section. So yeah, I'm breaking the rules just a little bit here by showing you future stuff, but whatever, it's fine. Again, mostly because I didn't pick the right function to use here. I decided to pick something that, again, just was realistic instead of something that was easy. Or at least looked realistic at the very beginning. Okay, so integration by parts is an interesting one. This says that if we have something like the integral of two functions, a u and a dv, then what we're allowed to do is take that and replace it with uv minus the integral of v du. So what does that do essentially? And you know, forgive me here. This is going to be it's essentially the reverse of the product rule. Essentially, but you know, don't quote me on that 100%. Essentially what you've got here is that like uv is equal to integral of u dv plus integral of v du. Give me 1 second here. Okay. So this is essentially what it works out to, that uv is equal to integral of u dv plus integral of v du, which again looks kind of like the product rule. It essentially is. We're not 100% we're not 100% going with it, but like if you took the derivative of both left and right, there would be some fundamental theorem of calculus stuff that you can work out, and eventually, yeah, it's the product rule. In this particular case, again, what we've got is we've got one side of it, integral of u dv, and then we can set that equal to uv minus integral v du, and it is intending on taking whatever u is, whichever u function you pick is, it's going to take this and knock it down to a du on the inside of an integral. So we want to intentionally choose something that is going to just kind of make it easier to take the integral. In the case of v, what we've got here is that dv is what we have, and then v is going to show up inside of an integral. So it has to be a function that is okay to take the integral on, and it's not going to make things worse. So what I would suggest is that because we have x as one of our terms, you should probably use x as u. Because, again, we're going to take the derivative of this thing and knock it down inside of the integral. And that's going to make it nicer and easier. If you try to do sine, think about what's going to happen. Your x is going to increase in power, and your sine is going to turn into a cosine. So then you've got an x squared and a cosine inside of an integral. So that is making things worse. So let's look at this. All right, integration by parts. What we had again was the integral of negative 2x sine of x. So then we're going to say that this is going to be equal to, and I usually like to make a little chart somewhere over on the side that says like, all right, u is going to be x. So therefore du is going to be dx. Nice and easy. dv is going to be this sine of x. And therefore v is going to be, well, that would get us a negative cosine. So actually, let's take that negative and put it with the sine of x. So then that makes v just be cosine of x. Move that over just a little bit. So then the 2 is kind of extraneous here. We're just going to kick that outside and make it 2 integral x no, we don't need that. X times negative sine of x dx. So then what that shows is that we're going to get a 2 times the quantity, right? The entire integration by parts stuff, u times v. So out of our chart here, u is just going to be x, v is just going to be cosine of x. So x cosine of x minus integral of v du. So cosine of x du is just dx. Well, that is a lot nicer, right? Taking the integral of just a single cosine is way easier than trying to do any of this other stuff that we had going on. So this is going to be 2x cosine x minus, when you take the integral of a cosine, it is a sine. So that preserves the negative that's out here, and we're going to bring in the 2 with distribution, so that's 2 sine x. Technically, at this point, there is also a plus c, because now we've got this integration that we're doing, but keeping in mind, we are doing this as a definite integral, so we don't actually need to do that. We don't actually need the plus c because it is a definite integral. Right, so for indefinite only, we're going to have that plus c. For a definite integral, we don't actually need to have it. Alright, so I'm going to cut this off way over here and magically write completely off screen. So, our negative 2x sine of x dx is going to become a positive 2x cosine x minus 2 sine of x. And then we're taking the integral of 4 pi sine of x, which is going to become a negative 4 pi cosine of x. Evaluated from 0 to 2 pi. Cut that right there. Okay, so This is the volume of this Hershey Kiss looking thing. Person's face, whatever you want to call it. I can draw, really. Alright, is equal to all of this stuff is equal to pi times. We can take all of these things, plug in 2 pi, and then take all these things and subtract 0, or you can do them individually. So we could do 1/3 x parentheses 2 pi cubed minus 1/3 0 cubed. Well, that one's nice and easy. Same with the next one. We get 4 pi squared times 2 pi minus 4 pi squared times 0. These are both going to be 0, so that makes it a little nice. And then here we get a plus 1/2 times 2 pi minus 1/2 times 0. That's 0. The next one's where it starts getting interesting. We get a negative 1/4. I lied, it's not that interesting. Sine of twice 2 pi is going to be 4 pi minus a negative, so plus 1/4 sine of twice 0 is still 0. And in this particular case, the sine of 4 pi is also 0. So both of these terms are 0. Alright, next one here is going to be a negative 2 pi times 2 pi squared. Minus a negative is plus 2 pi times 0 squared is, again, still 0. Plus 2 times 2 pi times the cosine of 2 pi minus 2 times 0 times the cosine of 0. Now this one is rather interesting because here we don't have something that is either just going to cancel out or something where one of them is just 0 because, I mean, in this case one of them is 0 just because. But looking at it, right, the cosine function at 2 pi and at 0 is 1. So in this case, we end up getting 4 pi out of this, whereas in this case, we get 0. I don't know. For some reason, that drew me in. I found it interesting. Here, we get another negative 2 times the sine of 2 pi plus 2 times the sine of 0, which are both going to be 0 again. All right, minus, where am I? Minus 4 pi cosine of 2 pi minus a negative is plus 4 pi cosine of 0. Now in this case, again, our cosine of 2 pi is going to be 1 and cosine of 0 is going to be 1, which leaves us with a negative 4 pi and a positive 4 pi, which are going to add up to 0. So, what do we get for all this? This is going to be pi times... Oh, no. No, 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 no. No, my mic's running. I'm seeing it right here. It's right there. Oh, no. Hang on. So, yeah, I'm getting it. I can hear it. I'm good. Absolutely. Go ahead and drop it in. I'm just gonna finish this up or something, and when you drop in your question, I'll just stop this. Okay, so we got pi here. This is gonna be times 1/3. The 2 is being cubed is 8, and pi is being cubed 8 pi cubed. This is 0, so that's gone. This one is going to be 4 times 2 is 8, and pi squared times pi is pi cubed. Yeah, you alarmed me. Can you hear me? Alright, then we got a half of 2 is 1, times pi is just going to be pi. That's gone, that's gone. This is now a negative. This is going to be 4 pi squared times 2 is going to be 8 pi cubed. And it's negative. Negative 8 pi cubed. So that and that are going to be gone. Then we get here a 4 pi. Woo! This one's a 0. That's all gone too. Okay. So that integral is to find the volume of this shape here. This is using what's known as the disk method, and can you hear me now? Sure hope. Anyway, yeah, we got, okay. So here we got 8/3 and pi to the 4th. And then here we got plus pi plus 4 pi is going to be plus 5 pi. So the volume of that like Hershey Kiss sort of shape there is that thing, which is pretty nasty. Yeah, so this is Calc 2 stuff generally. I did it in Calc 1 in high school, but we had a year-long course instead of a one-semester course, so like I don't know where I started and stopped comparatively. I think we sort of did like a semester and a half worth of college material in 2 semesters of high school. Whatever, you know. Calc A, B, and BC, we sort of did A and B and maybe sort of C. I don't remember. Yeah. Anyway, yeah, so the disk method is taking a shape, whatever it might be, and splitting it up into disks. And so we're saying like we're going to take the area under the curve and then extend it into rotating it around the x-axis to make a disk like this. And so this is going to be like the infinitesimal part of the whole. And then here, all we're doing is we're saying, well, how do you find the volume of a cylinder? Well, volume of a cylinder is the area of the face times the height. So the area of the face is going to be your radius, f of x, squared, times pi, times the height of the cylinder, which is dx. And then we're saying that we want to add all of them up over this entire area, so you take the integral of this thing from A to B. Whoa. Okay, so that... Oh. That's not good. Okay, there we go. Sorry, I'll leave that there if you... Right. Okay. So, real numbers. X, Y, and Z. Such that X, Y, and Z are greater than 0. And the distance between any two of them is less than 2. Okay, so then prove that sigma, like the sum okay. Is there something that comes... I'm not seeing it, sorry. Are you saying that sum like this? Square root x, y plus 1. Get that much anyway. And then is there something that connects them, like equals or less than? Oh, less than or equal to. Okay. Sorry, I thought that was an arrow for a second. Less than or equal to the sum of... Is that what you have? Alright, no Christmas music. Seriously. We can come back to that later. Like, in November. Christmas in July. Yeah, happy July, by the way. I'm also having a bit of a hard time straightening my arms because I'm old. I attempted to work out the other day. My wife said, yeah, that's your first mistake, trying to do a fitness. It wasn't that bad either. It's only when I want to straighten my arms that's terrible. I was just walking on the treadmill and like lifting weights, and that's it. And now my arms hurt. I mean, realistically, I just need to get the tiny weights now and do those like 100 times, and it'll be fine. So, Kiwi Gamer, I just need a clarification if that is what you have. That that is what you have. I'm guessing that there are other ones in here that involve Z. It's just that this one they didn't want you to. Yeah, okay. So the sum of all possible x's, I think, are going to be less than or equal to the sum of all possible square root of xy plus 1? Maybe? I mean, if you had a finite list, you could do it in programming. Say like, okay, sum up all the x's, then here, sum up all the x's and y's as like a, well, I would do it as a for loop, but that's awful. Other people could do it much more simply with some other, maybe a while. But anyway, how to do it mathematically, yeah. Yes, okay, fair enough. You're not an engineer. You're not a programmer. I'm guessing the four-color theorem also might piss you off a little bit. So, Ken Appel and, oh, nuts. I figured this, alright, I looked at the history of this a while ago. Yeah, so all possible xy plus 1. Yeah, definitely. I did, in fact. So, I took one semester of... So I took one semester of neural networks, and so that was doing the very basic of machine learning, and there was a lot of sums as we were going through it, because basically you're looking at like you know, taking a series of inputs, and then all of them are feeding to, let's say, 2 outputs. Like this. And so every single one of these, when you look at the weights, this is a weight that is going from I to j, and so this is going to be weight 1, 1. This is going to be weight 1, 2. This is going to be weight 2, 1, weight 2, 2, etc. And so you're going to have all of these things that are, you know, have these i's and j's at the same time. And then also you're going to have inputs, which are going to be x sub 1, x sub 2, x sub 3, and then y sub 1, y sub 2 being your outputs over here. So, go for it. So y1 is, for example, going to be x1 times the weight 1, 1 plus x2 times the weight 2, 1 plus x sub 3 times weight 3, 1 plus x sub 4 times weight 4, 1 plus x sub 5 times weight 5, 1. And then you can shortcut this by saying that y1 is going to be equal to the sum of each x sub I times w sub I1. Or then you could shortcut that by saying this is going to be y sub j is going to be sum of x sub I times w sub ij. How can you be a better problem solver? This is a much bigger question. Yeah, I mean, this is a huge question. So, I get students all the time who want to be better problem solvers. Most of them just don't know that that's the question they want to ask. Most of the students actually ask, how can I get a better score? Okay, give me 1 second here, and hang on, real quick. So anyway, yeah, that is a really good question, and I'm not sure that I am even necessarily qualified to answer it that much, but I mean, the main answer is going to be like practice, 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 but of course that's not really helpful necessarily. So, like, the most basic thing that you can do is start by laying out the individual problems and saying, like, you know, what are the things that you know? Or what are evidence? What do you have for evidence? Or what are the things that are given? You know, things like that. And the next step is really like being able to see what your goal is. Yeah. You're also young, so I mean that is a big help. If you were like my age and asking that question, it's maybe a different set of answers, but so know the evidence, know that what you're given, what is it that you know, and then look at the goal that you have. It's like, where are you trying to go with this? Then from these two pieces of information, this is where experience comes in. So having seen different problem types and having seen having seen different pieces of information, having seen different problems before, coming from these two pieces of information, you might be able to work either from what you know and work toward your goal, or start from the goal and say, well, what are some smaller goals that I need, that I have? So instead of like making this big connection between what you know and what your goal is, again, this right here might be its own little microcosm. You might say, okay, here's what's given, here's the goal, and now we're going to split this up into sub-goals. So like this is going to be goal 1, goal 2. You're probably going to go from the end and start labeling them this way. You say like, okay, what are some small goals that I can get from the beginning, or what are some slightly easier goals from the end, which again, having gone through like a proofs class, it's really helpful to see from that perspective and say, okay, I know that I need to, you know, I don't even know here. I need to prove this thing, right? Right. How do we do this? Okay. We look at all possible x's, and we need to sum them up. And we need to prove that that sum is going to be less than or equal to the sum of the square root of x times y plus 1. All possible x's times all possible y's plus 1, taking the square root. So, what might be some small goals for this one? I've never actually seen this problem before, so this is going to be an interesting one. I have no guarantee that I'm going to be able to solve it. So, like, take some of the other stuff that you've seen in this same chapter, or maybe in previous chapters that look roughly similar to what you... yeah. So, like, I mean, eventually I'm going to be able to solve it, but it might take me, like... it might take me weeks just because I'm not paying that much attention to it. Okay. So what are we going to get out of here? Fair enough. Racing me. Yep, yep. Like I said, fair enough. So in this, I might say, for instance, that I want to show that this number is going to be big, or at least bigger, than this number. So how am I going to do that? The product of two numbers, which are at all going to be greater than 0, and also the numbers themselves have to be within 2 of each other. So one possibility would be, I might say, if x minus y is less than 2, and I know it's the absolute value, but let's just assume for a moment that so these are going to have a symmetry to them. It might be the other way around. I don't know. Hang on. We'll figure it out in a sec. This is the other thing. Don't get caught up on little semantics. It's fine. You can work it backwards later. Like from the beginning? Oh, okay. Yeah, so this is another option. Is that when you're solving a problem, you can say, well, are there cases that I can split it up into? Like you did. That's perfect. So assume these 3 cases exist. And yeah, if we have sum of x equal to sum of the square root of, if, let's just go with equality first. Because again, so this is going to be like x squared plus 1 That's fine, you're fine. Okay, so yeah, in this particular case, you can just say that individually, square root of x squared is going to be less than or equal to square root of x squared plus 1, and therefore the sum of all x squared, square root of x squareds are less than or equal to the sum of all square root of x squared plus 1. So yeah, you got that one. And you said the other one was x less than y right. So you call this one an upper bound. Wait, what? You might have to use this, is what I'm really saying. So replace y with x minus 2. So x times x minus 2 plus 1. This is x squared minus 2x plus 1. It's going to be less than or equal to the sum of square root of x minus 1 parentheses squared. Okay, now, hang on. That yeah, that didn't quite work the way I wanted it to. I mean, it's probably because of the absolute value. It's not technically quite the way that it should be here. Oh, x is let. If x is less than y, then the absolute value of x minus y is going to end up being, right, we need to shift it around. It needs to be the negative parentheses of this. It'll be 2 minus x, right? Technically. Okay, so with x less than y. Alright, so here's the thing. I have been harping on this for a long time, and I didn't do it. So, this is my fault. So hang on, let's go about this correctly. If x is less than y, then the absolute value of y minus, or x minus y is actually going to be y minus x. So y minus x is less than 2, which means that we can trade this around for x plus 2. Y is less than x plus 2. Which is the sum square root x plus 2 plus 1. Now this is the sum of, here we go, x squared plus 2x plus 1, which is square root of parentheses x plus 1 squared, which is sum of x plus 1. Alright, cool. Good times. Yeah. I'm getting there. Alright, so then... that's that case. So then y is less than x. So it says that x minus y is less than 2. That's this actual one. So presumably what you're saying is that this doesn't work quite this way. It's not quite that easy. So y is going to be greater than x minus 2. Which makes this a lower bound for what's actually going to happen. So then this is going to be x times x minus 2 plus 1. Yeah, this is the problem I was having before, I think. Is that this isn't actually necessarily going to be in the center of these two. Is that this is going to be on the other side. So I'm using the consequences of the absolute value here. Is that y is less than x, therefore this is going to be a positive number. Or is that it? I mean, I already know y is less than x, but anyway. X is less than y plus 2. I could do that instead. It's not quite in the same... that's fine, whatever. We'll make it work. This is going to be y plus 2. It's going to be greater than that sum. It's going to be x is y plus 2 times y plus 1. Okay. Right, in theory? Is that going to work? Maybe? No, because that's going to just be y plus 1. This is the sum of y plus 2. This is the sum of y plus 1. So now I'm backwards. That's really not good. Get it? Next question, is that true? Even if I do that. I'm replacing x with y plus 2, which is greater than that. So that's actually not going to help, because this is on the outside, setting an upper bound for this thing. So that's actually not good. Really, this is what we're trying to prove. And in my stuff, I appear to have proved just the opposite. So that seems like a problem. Alright, number line wise. I have here, this would be like the sum of all y's, for example. Would be down here. Sum of all x's would be in the middle. And the sum of all y plus 2's would be up on the higher side. No, it'd be perfectly fine to break it up into more parts if that serves your purpose. How do you mean greedy? So we know that this has got to be the square root of xy plus 1, the sum of, and then the sum of all square roots of y plus 2 times y plus 1 is going to be somewhere bigger than that, but we don't know exactly where. In theory, we could also say that the sum of all, if we just replace x's, if we just replace x's for y's, then we end up with like y squared plus 1 here. And this is, yeah, okay. This is y squared plus 2y plus 1, which is bigger. It's like that has got to be there, and this has to be in the middle somewhere. But then we have to figure out where these two compare to these two. Problem here seems to be like this is here somewhere. I guess technically right in the middle of y, right in the middle. Sum of y's and sum of y plus 2's. Doesn't matter. Arithmetically speaking, this is going to be right in the middle here, because this is equivalent to the sum of square root of y plus 1 squared. So this is going to be just the sum of all y plus 1's. So that's exactly in the middle of sum of all y's and sum of all y plus 2's. Sum of all y squared plus 1. We can't compare to these right now. I guess we know that this is greater than this, somewhere-ish. We don't necessarily know where it is in comparison with the sum of all x's. So that's really the problem. Is it there, or is it there? And then is the sum of all x's truly here, or is it also like out there? We don't know that either. So yeah, that becomes a problem. I'm trying to figure out on what side of all this stuff does it lie. It's not quite as straightforward as the one above it. Like if I just change this the other way around, focus on x's again, then it's still going to be focused on x's. Again, this is 0. Let's go with 1. y minus 2 is less than x minus 2 less than y. Go for it. I mean, honestly, a lot of math ends up working out that way. So it's like, wow, that's... Or why didn't I think of that 20 minutes ago? Or... No, I know I just did this, but still. So we want to prove this. Using this stuff. Wait, did I just do it? No, not necessarily. Okay. Alright, so we know that the sum of all x's is less than the sum of all y plus 2's. So here if we do this, sum of all x's, we want to prove, we haven't done it yet, sum of all x's is less than the sum of all square roots of, here we go with y plus 2 be on the upper end. We actually want the lower bound, I think. Right, what's the smallest value that this could possibly be? Yeah. So then we want x x minus 2 plugged in here, but if we do that, then we get x minus 1 parentheses squared, and we get x minus 1 coming out of it. Alright, Kiwi Gamer, what did you get? So I'm just running in circles here. Doesn't look like it, right? Because my problem is that if I plug in the y plus 2 stuff here, this is actually bigger than the x value. So actually that is kind of better, because if I plug that in here, that's going to make this bigger than it actually is. Which, in theory, could be better. And then over on this side, the problem is that if I plug in the like x minus 2 stuff or y minus 2 stuff, it is actually smaller than this other side, which is contradictory to what we want to find. So like we've got this ambiguous area where we don't know where the square root of, or where the sum of x's are. It could be here or it could be like here. It's just between the sum of all y's and the sum of all y plus 2's. This stuff down here is the sum of all square roots of y squared plus 1 is going to be the smallest thing that we can get, which has to be bigger than the sum of all y's. But we don't know how it compares to the sum of all x's. I mean, yes, but the other thing I was thinking is there like another problem that uses the exact same stuff, or is it just randomly that we have 3 inputs in this particular thing? Because you're right, if there is a third input and it's just for, okay. Because it could be, in theory, that you're going to end up with, like, spheres in a three-dimensional space. And then you're trying to figure out, like, where are these things? This could be X. This could be Y. Right, this is less than 2, this is less than 2, this is less than 2. Yeah, I wasn't really thinking calculus, I was just trying to figure out, like, you know, does this need to be a two-dimensional space? But I think it's just one-dimensional space, so it should be... so it should entirely be on just a regular number line, and then you've got, like, an X, a Y, and a Z, like this. And then you know that the maximum distance must be less than 2 between first and last. may have to try this out over the next week or so and see what's going to happen. I imagine there's going to be a lot of scratching out starting over. Yeah, so I suspect this needs to be proven that it's within certain bounds. So like I was saying over here, if we can get sum of all x's to be between, guaranteed between, square root of y squared plus 1 and square root of y squared plus 2y plus 1, or y plus 1. If we could get sum of x to be bounded between those two, then it's going to say, like, well, it has to be not necessarily, though. Oh, man. Yeah, this is a good one. Good in the sense that it's going to take a while to really work out what the solution to this problem is. But yeah, with the z being in there, it seems like it shouldn't be a red herring, that should potentially be used, in which case it might be worthwhile to try and figure out, like, okay, if the distance between x and z is this maximum bound of 2, then how does that, and it's going to be the other way around if we did y is less than x. So, this one there. Yeah, I'm going to have to think on this. I think maybe using the intermediate of z is going to have to be the case. Since the distance between x and z, must now be less than the distance between x and, y and z. This might be able to yield something. Right, by definition. Oh, no, because if z is on this side versus on that side, which, yeah. I guess technically now we can break this up in the second case. So z is over here, and then we got y, and then we got x. In this case, distance between x and z is going to be greater than distance between y and z. Okay. We might have to split that up into two separate cases and then figure out how that works. That will be interesting. All right. Why don't we take a week and think about it? And I'll get back to you hopefully next Wednesday. I need to remind myself to work on this between now and then. Oh, wait. Wait. You get it? Okay, answer me one thing. Are you using this same method or this line of thinking? Not even close. Okay, cool. Alright, we want sum of all x's less than square root of x plus 1. Yeah, no, I believe you. See, if x is greater than z plus 2, z minus 2. If y is also greater, z minus 2. Plus 1. Still technically don't know this part. So this feeling that you've got right now where you're like so close, this is probably the most exciting part. Right now I want something that's bigger than the sum of all y's, but definitely still less than this thing. I just want it to be the square root of z minus 2 squared, but that's not going to be true, because although it will be much less than this, it won't be greater than the sum of all x's. It's going to be less than the sum of all x's. So that's what's trapping me here. And we still got one more case to get through anyway. smaller than x times y, that's going to be y squared. So now we got to prove that sum of all z plus 2 is less than the sum of all square roots of y squared plus 1. Something crazy here. If we make a negative y attached to all these things, now you can't add it into the sum. Never mind. That's the sum of all negative y's. Oh man. Alright, so if they have the same indices, you can combine them, which is going to make this the sum of all x minus y's. Then, sum of all z minus y plus 2's, less than, this is the one we don't know, all y squared plus 1 minus y, which is the square root of y squared, equivalent. Getting anywhere, Kiwi Gamer? Frustratingly really, really close. Make it interesting. Curses. That also happens. Sometimes it gets that way. Yeah, there's some heavy algebra in here, and it's not coming out, at least not the way I want it to. So, yeah. I'm gonna have to look over this for the next week. Remind myself that I said that I was gonna look over this for the next week, and see if we can at least get somewhere with it. So, well, thank you for showing me this, because this was fun. Alright, so we're going to hop on in and raid. Let's see. Well, Jason Charles Miller's just about done with his. However, hop into Dariosa's channel for a raid tonight. She is doing Breath of the Wild, looks like. Yeah, she's doing Breath of the Wild tonight. So, gonna hop into her channel and check that out. She's great. She's entertaining. And she gets a huge number of subs from her community, and she's like this close to crying almost every night. Anyway, she also just made partner, so giving her some attention. So, Kiwi Gamer, thank you for coming. Everybody else out there who stops in for the video on demand, thank you also for coming and watching this parade through algebra that we're making here. Yep, have a great night, and I will see you all around the Twitcherverse, I'm sure. This is Obi-Wan Pez for and Simplex Pachinko. Good night.